From Los Alamos National Laboratory, this is the National Security Science Podcast.
That's kind of the whole spirit of this place, is to just get things done quickly. It's kind of as much of a startup kind of agile approach to manufacturing as we can have.
Manufacturing really is the backbone of any production. Here we're really focused on making perfect parts.
Hello, and welcome back to the National Security Science Podcast. I am your host, Brenda Fleming, and this is the podcast for the National Security Science magazine. We are recording from Los Alamos National Laboratory in beautiful northern New Mexico. Today, we explore a little-known facility at Los Alamos National Laboratory that's manufacturing non-nuclear parts for the nation's nuclear weapons stockpile. But before we jump into that, let's first turn things over to National Security Science writer Ian Laird to hear today's Labcast, a minute to highlight current achievements at Los Alamos.
A Los Alamos National Laboratory postdoc recently made a discovery that will shine a light on how the universe formed. Madeline Marshall used the James Webb Space Telescope to identify a supermassive black hole. Scientists originally discovered the black hole in 2011. At that time, it was the most distant black hole ever identified. Now, Marshall has measured the mass of the stars in the galaxy in which it resides, revealing that the black hole has roughly half the mass of the stars in the galaxy. It is approximately 1,000 times larger than black holes in most galaxies with comparable numbers of stars, which makes this the highest black hole to galaxy size ratio ever measured. Marshall also observed that this black hole's host galaxy is merging with another galaxy. The next step will be continuing to make measurements to support theories of how the first galaxies and black holes formed in the early universe.
Thank you, Ian. Recently, the National Security Science magazine team toured the lab's Mark Quality Manufacturing Center, or MQMC, where employees make some of the non-nuclear parts for the United States nuclear stockpile. National Security Science writer Jill Gibson takes us inside the MQMC to meet the people making these perfect parts.
That's the sound of manufacturing at Los Alamos National Laboratory, specifically the manufacturing of parts that will go into nuclear weapons. Although most non-nuclear parts and components are produced at the Kansas City National Security Campus, the need arose for a small, fast-moving manufacturing facility that could support alterations on certain weapons. Los Alamos National Laboratory stepped up to meet that need. Our tour of MQMC began with introductions and an overview of exactly what the facility does.
So I'm Ike Timko, product process manufacturing engineer.
And then Scott Schaefer, kind of the same roles as Ike. I've been here for 2 years as well, covering a lot of the manufacturing, engineering roles and project management roles.
We started up, so a lot of the funding to stand up the MQMC, which is this kind of state-of-the-art manufacturing facility, was provided by the W88 for the Alt 940 project. We kind of put our foot in the door and said, hey, we can be agile, we can stand this brand new capability up and provide these parts for you. And so that's kind of the whole spirit of this place, is to just get things done quickly. It's kind of as much of a startup kind of agile approach to manufacturing as we can have. And so that's, I think, really where we're unique as a manufacturing facility. So we are equipped to perform machining, assembly, and inspection of war reserve product. So any product that will go directly on a weapon system. So from raw stock to a finished assembly.
A nuclear weapon requires thousands of parts, and some of them are tiny parts, like screws and washers. But when you're assembling a weapon, you can't just run to the hardware store and pick up a box of screws. Even the most tiny parts must be manufactured and inspected to ensure they are precise and correct.
So we start, we get a drawing from a customer,
and it has dimensions on it, and they say,
yeah, I need something that's of quality to go on a weapon, and it goes into our shop. So they'll give us a drawing, and then we have to figure out how to manufacture it and inspect it. And so the inspection lab is really so that we're checking all the features on this drawing to make sure that they fit tolerance. We move fast here. And so that's the theme, right? Is we're quick, we're agile, we do things quickly, we're efficient, at least as efficient as we can be, or try to be. So we're cranking parts out constantly. And so we start from raw stock, like a block of aluminum, and out the other side comes finished assembly. So it's pretty exciting.
Ike and Scott take us into the shop area where machinists are making parts using computer numerical control machines, or CNCs. We're joined by shop supervisor Bob Kwolek and machinist Marshall Maez. The team explains that each CNC machine works slightly differently. Some use electrical voltage to cut metal. Others use sharp tools. One thing they all have in common, all are computerized.
This is basically you program everything in, it's ready to go, and then you just make sure it's doing its thing.
yeah, so there's a function on the screen where you can chart out where it's going to trace. You can plot before you run it, because obviously you don't want to get 15 and a half hours into a cut and realize you've done it wrong. So we use tools like Vericut and the machine controller to simulate the movements and make sure everything's operating correctly. And then for a cut like this, it took like 16 hours. We raise up the gate to block the water, fill it up, and push go, and it does its thing. And when it's done, it shuts off and parks, and then we can go get the part. But all that is, proper programming.
Right.
So, and that's the nature of manufacturing now. CNC machines do a lot of it themselves, but the difficulty is getting them set up correctly.
Here is a small lathe. You stick a piece of round stock, like that big bar or a small rod or something. It's loaded into the machine, and the machine spins that rod or bar. And then you take something like this, just a single pointed cutting tool, and as that part is spinning, you drag this cutting tool across it, and it cuts the metal off that bar.
That's a cutting tool?
Yeah.
So what's it made out of?
Yeah.
They can be made out of different materials. Sometimes it's high-speed steel. Sometimes it's got different coatings on it. Sometimes it's ceramic. It's got a round edge there, but it's very sharp on that point there.
Yeah.
So as you push it into there, it kind of peels material away. So lathes are really good for making different kinds of round parts.
As we continue to walk around the shop, we see and hear each machine in action.
So since right now we're cutting titanium on this machine, it's a potentially flammable metal. So we have to keep up these guardrails, contain it in a flammable chipped container, just to prevent any fires.
This machine is a mill. It holds the workpiece stationary and then takes some kind of cutting tool. So your workpiece is stationary, usually kind of more square profiles. You can cut kind of any geometry you want, but you typically start with kind of a square piece of stock. So something like this plate, it holds that piece of stock stationary, and you load a tool up in the spindle, and that tool spins. So now instead of the part spinning, your tool is spinning, and you use this kind of edge to cut your part.
What's the average size of the parts you make in something like this?
That's a trick question, right? Because we've made parts in that machine that are less than an inch in diameter, teeny tiny little parts. So on that machine, we're making teeny tiny little screws out of titanium. And we've also made parts on that machine that are much bigger.
2 foot.
We can make larger geometry parts that kind of are 2 to 3 feet long, about 24 inches in diameter, and so we can regularly hold tenths of a thousandth of an inch, so 1 or 2 10,000ths of an inch in dimensions on this machine. So super tight tolerances, over $500,000, $800,000 machine, state of the art. The goal here is to be as quick and as diverse and agile as possible to be able to produce the parts that no one else can or wants to touch.
We pride ourselves on being able to be very reactive to our customer base.
And so we've got a really great dynamic in the shop. Manufacturing really is the backbone of any production. Here we're really focused on making perfect parts because the risk is really high. The thing about manufacturing that's most exciting to me is being able to turn a chunk of metal that just rolled off the kind of foundry line into a complex custom part. And it's pretty exciting to look at a stack of raw stock and see that it produced an assembly in the end.
This room is very noisy. What is all the noise we're listening to?
So each of the machines have compressed air and hydraulic pumps that run all the systems that move the machine. There's electronic servos that actuate it. Every machine has cooling systems. There's coolant pumps, so each of these machines, you can see this milky white stuff that sprays out everywhere. That's to cool the part, because when you're shearing off all that metal, it gets really hot. And so we have all this coolant that sprays on there. And so all this noise you're hearing is just the machine's heartbeat.
How long does it take it to do its thing?
This part actually runs for 3.5 hours. So yeah, we have a smaller part that bolts onto it. It takes an hour and a half.
So this is what it looks like. You take a part like that, and it produces a bunch of chips that look like this. And so this is coming off that machine, little curly cues of aluminum. And they're actually super light. It's like steel wool.
Yeah,
this is
like the scrap.
This is the chips from the parts that we are machining.
So you can, any configuration that you can imagine, we can get a tool in there somehow.
Yeah. The magic, the goal for modern machining right now is just reducing the setups. The less setups that you have to do, moving from one machine back to another, and do this feature over here, and then gotta have that machine to do that feature over there. We do about like 99% of this part here.
In other words, if you did one op in one machine, another op in another, every time you load it, potentially you're drifting from that true position. If you do everything in that one setup, everything is usually perfect to its perfection at a reasonable cost.
To guarantee that perfection, every part manufactured must undergo inspection. That's why the next part of the tour is the MQMC Inspection Lab.
It's precision controlled, industry standard relative temperature, so 20 degrees Celsius plus or minus 1, so it's always the same temperature and humidity in there, and it has class 10,000 particle cleanliness, so it's state-of-the-art inspection lab.
This is Steve Pattinson. He's the inspection shop supervisor.
The machines are phenomenal. We calibrate our own machines because they're on a classified network. We can't have the manufacturer come in.
So these machines, their entire job is just measuring.
That's all they do.
Okay.
Yep, three-dimensional measuring. Saying 1 micron plus L over 700, which means if you measure from this corner of the machine to that corner of the machine with the standard, the spec is about 2.5 microns. I don't know if you know what a micron is. Take a piece of paper, section it 100 times, that's 1 micron. The thickness.
That's crazy.
Instead of just doing it once and say, oh, I got lucky, it's good, you have to do it 3 times. Every measurement you have to do it 3 times during the calibration process.
So how many do you throw back and say, oh, didn't make it?
Not very many. We get one once in a great while. We collect, I'd say, thousands of dimensions per assembly, and it's all done electronically. These parts have touch, probability, and scanning capability, so you can just scan the ball, you can scan the part.
If the temperature in the room goes outside our acceptable standards, we have to recalibrate the machines. Every time there's a deviation in temperature, Steve and his team have to recalibrate. And it takes a week to recalibrate a machine.
It takes weeks.
The National Nuclear Security Administration, or NNSA, which is part of the Department of Energy, or DOE, and oversees the lab, has given a special authorization to the MQMC. This authorization allows the MQMC to literally give each part a final stamp of approval.
And the NNSA was actually so pleased with our ability to reliably provide quality product that they gave us full diamond stamping authority. Diamond stamping is the way the NNSA, the DOE, buys off on a product and says, yes, this is mark quality. This is weapons quality. It's basically a seal of approval from the DOE.
Is it an actual engraving or stamp that goes
it's
on
a
the
stamp,
part?
yeah. It's a black stamp that looks like a diamond. It's a it's a big deal. That's the final check saying you made the product, it's perfect.
The MQMC also maintains rigorous quality standards when storing manufacturing process data. The staff uses specialized software to compile detailed records that accompany every part. Every aspect is aimed at creating a highly efficient facility that can adapt to multiple demands and projects and support the national security mission by making perfect parts.
Thanks, Jill. You can read more about MQMC and other types of manufacturing in the Winter 2024 manufacturing issue of National Security Science magazine. Now, before we sign off, we'll turn things back over to Ian for our highlights from the Hill.
7 researchers were named 2024 Los Alamos National Laboratory Fellows in November. Laboratory Director Tom Mason commended their lengthy bodies of work that have contributed to the lab's mission and scientific community. Fellows are judged and awarded on 3 criteria: sustained achievement or leadership in their STEM field, a breakthrough discovery or invention that significantly impacted or advanced their field, and recognition throughout their field as a leading authority through awards and engagement. This year, fellows were recognized in fields ranging from a variety of disciplines, such as quantum technology, plasma physics, and disease modeling. The fellows are Malcolm Bosher, Luis Chason, Sarah Del Valle, Rod Lynn, Kevin Mitchell, Cynthia Reichard, and Robert Aiken. Aiken was recognized for his work on solidification science and gravity casting for uranium alloys. If you want to learn more about Aiken's work in uranium casting, you can check out NSS Magazine's Manufacturing issue, where editor Whitney Spivey wrote an article on the Lab Sigma facility where this takes place.
Thank you so much for listening to the National Security Science Podcast. Don't forget to check out the National Security Science magazine online at lanl.gov/magazine to learn more about how better science equals better national security. For more great stories from Los Alamos, including several other podcasts, video series, and interactive stories, visit discover.lanl.gov. That's discover.lanl.gov.